Hello, Mr. Betts here. Let's take a look at a few examples where we're using the limit comparison test to see if a series converges or diverges. Remember, the limit comparison test is a little bit more powerful than the direct comparison test, so we can always get a conclusion from our result as long as we make a good choice with our comparison series. So what I'm going to do is I'm going to look at what dominates the numerator and denominator, and I'm going to compare it to that series. So I'm going to compare it to 10 to the n over 7 to the n, which is the same thing as 10 sevenths to the n, which is a geometric series with common ratio of 10 sevenths, which is greater than 1, which means that this series itself is going to diverge. Now, I'm not quite done, but as long as this comparison series is valid for this test series, they're both going to do the same thing. So our test series should diverge as long as this was a good choice. What I need to do is I need to find this limit that is looking at what happens as n approaches infinity of the test series over the comparison series. So this is the same thing as the limit as n approaches infinity of 10 to the n over 7 to the n plus 11 times 7 to the n over 10 to the n. Now, 10 to the n part, that's really easy. Those just cancel. The 7 to the n part, we have to look at relative rates of growth, also called dominance. So the 7 to the n is going to dominate the numerator and denominator. So when n gets really big, they're both going to behave like 7 to the n. This limit is 1. So since that limit is non-zero and finite, then that means that our comparison series and our test series are both going to do the same thing. So this series is going to diverge by the limit comparison test with the series 10 to the n over 7 to the n, which diverges by geometric series test. And I'll put r equals 10 sevenths, which is greater than, doesn't matter if it's greater than 0, it's greater than 1. And there you go. I do want to point out that from the very beginning, we could have used the nth term test for divergence to say that this series is going to diverge, because as n gets really big, the terms do not approach 0. So 10 to the n over 7 to the n, with n being some big number, is actually going to be a really big number, not approaching 0. So the limit comparison test here is not necessary, but it works. This one we're going to compare to n over n cubed. So we're going to look at the series n over n cubed, which is the same thing as 1 over n squared, which is a p-series with p equal to 2, which is greater than 1. Remember, with a larger p-value, the denominator is bigger, which makes the term smaller, and this is going to converge. So again, if I've made a good choice with my comparison series, then they're both going to do the same thing, and our test series should converge. So let's verify that with the limit. So our limit is going to be the limit as n approaches infinity of n plus 1 over n cubed plus 6n plus 3. All of that over, and I'm actually going to use the 1 over n squared version of it, 1 over n squared. So this is the limit as n approaches infinity, n plus 1 over n cubed plus 6n plus 3 times n squared over 1. So if we look at relative rates of growth here, our largest term is going to be n squared times n, which is 1n cubed. Our largest degree term in the bottom is also n cubed. N cubed divided by n cubed is 1. So since that limit is not 0 and not infinite, then both of these series are going to do the same thing. So this series converges by the limit comparison test pardon my sloppy writing, with 1 over n squared, which converges by the p-series test with p equal to 2, which is greater than 1. And the last example we're going to do, this one I'm going to compare it to 1 over the square root of n squared, which is, with n being a positive number, is just going to be 1 over n, which diverges. And we could say p-series, or we could just say harmonic series. Harmonic series is a series that we can just identify as harmonic, and we know it diverges, so that's enough. So if we look at our limit, what's going to dominate the bottom is going to be the square root of n squared, which is n. What's going to dominate the top is also n, so that limit is 1. So this series diverges by limit comparison test with, I'm just going to identify it as the harmonic series, and that is going to be enough. I do want to point out that the limit comparison test works as long as this limit right here is any non-zero finite constant. However, when we make our choice for the comparison series, usually we're going to choose one that limit is 1. However, if, for example, this were a 2 on top here, and we got a 2 here, which would put a 2 here, which would make this 2, I would still use the harmonic series for this. And that 2 is just telling me that the series is going to behave like double the harmonic series. And since the harmonic series has an infinite sum, it's going to have roughly double the sum, which is going to be infinite also. So even if I choose a comparison series where this limit is not 1, as long as it's any finite non-zero number, then this series works. Or I'm sorry, this test works.